There we go. All right, so let me share my screen. We're going to go over a few examples of subnetting because last week Mark kind of hit you with a shotgun blast of all the different IP addresses and different subnet masks and all that type of thing. So I figured I'd go over a few examples, real world type stuff, to try to put things in perspective and then answer any questions you guys have along the way. So let's begin with. There it goes. Okay, so say we have, let me go back. Minor technical difficulties. Okay, here we go. So say we have this network here. You've got a router and some switches and another router and some switch with some computers attached to both of the switches. We've got IP addresses in different ranges. If you remember what the /24 means, anybody out there that refers to?
That's the CIDR annotation?
Yes.
CIDR, okay.
Yep.
Go ahead.
So what that means is that the subnet mask in decimal would be 255.255.255.0, and in binary it's basically 8 ones, another 8 ones, and another 8 ones, an octet. Those are also, how many bits are in a byte? 8. So we got 3 bytes of ones and then 1 byte of zeros. And that would be all the networks, and that would be the nodes. So in these networks that we have here, the /24s, how many devices do we have on each of those networks? You want to take a stab at it? No, you're muted, Jonathan. I see you talking. You're still muted.
Yeah, now I'm off track here because I don't know. I'll just say I don't know.
Okay, all right. Well, it would be
239.
What did you say?
239. So it's 512.
239.
2 power to the 9 minus 2. So it's like 510.
No.
No. Okay.
So
You have 9 zeros there, Peter?
no, it's only 8. Should be only 8.
3,
Maybe I do have 9 zeros.
5, 6, 7,
Yeah,
8, 9.
that's.
You got 9 zeros.
Hey, I got it right.
All right, I mixed.
You did get it right, but
Good eye, Gary, for counting my zeros, but
yeah,
really
I count
8.
every single one of them.
Yeah, we need one less
All
zero.
right, catching my mistake. Good job. All right.
Yeah.
So if it was 9, then yes, you're right. It would be 510. But in this case, it's actually 254. Does that make sense? Okay.
Yeah.
Yes.
All right. So 254. That would be 2 to the 8th minus 2. So you have to use an address for the network ID, which in this case is 0. You have to use another address for the broadcast, which in this case is 255. And then the number of networks is 16,707,216, which is 2 to the 24. Does that make sense?
Yeah, this number I couldn't wrestle, so yeah, thank you.
Yeah, I had to put that one in the calculator. So, all right, so let's concentrate on these 2 sections of the network. As you can see, we're on 192.168.1.1 and 192.168.2.1. So we have 2 separate networks, and then we're trying to communicate with them between 2 routers. So because a switch won't pass onto different networks. It just only will pass along its own network. It only talks in MAC addresses. It doesn't pay attention to the IPs, and the IPs have to match on the network in order for them to communicate. So these two computers can talk to each other, and these two computers can talk to each other, but this computer cannot talk to this computer. So in order to make that happen, we have to get these routers to talk to each other, and they have to be on their own little separate network. So in this case, we've got 192.168.20.5. Now, what is the minimum number of nodes in a network can we do? Do we want to take a guess?
Question, we're dealing with like technically dealing with like 3 separate networks here.
Yeah, exactly. And so we're trying to configure the third one because the other two have configurations correctly. But the third one, we're missing a number here. And we're also missing the subnet mask for them. So we're trying to figure this out. But we know we want to use 192.168.20.5. What would the other one be? And with a minimum number of nodes. So the minimum number would be 2. You can actually get 2 out of 1 bit, you know, on and off, a 0 and a 1. However, in order to make that happen, you actually have to use 2 bits. 1 bit for the nodes and 1 bit for the network ID and broadcast ID. So a total of 2 bits. So 4 addresses, in other words. So CIDR notation would be a /30 because you've got 32 total bits normally. But if you're only going to use 2 of them for your nodes, then you have 30/30 for your the networks. That makes sense? So what would the subnet mask on that in decimal be? You want to take a guess? Get a subnet calculator out.
252.
Yep, 252.
How'd you get 252?
So first bit will going to be 1, the second bit will going to be 2, and total 255 minus 3, 252.
Yep, that's exactly right.
Or we can add everything besides 1 and 2, but
Right.
Either way, yeah, right.
So the number of networks then is 1,073,741,824. Big number.
Yeah, so this is a good point that Peter brings up. 3 networks. This one network in the middle, just to connect these routers, is a separate subnet because every interface on a router has to be a separate subnet. So there's only 2 nodes on that middle network, and it's 20.5, is it 20.5 and 20.6 or 20.5, 20.4, but it's just those 2 IP addresses, and that's it. That makes up a subnet. So it's so we've got subnets that have no nodes, no laptops or other things on it. It's just 2 endpoints.
Yep. So what is the other number? Is it a 6? Is it a 4? What do you think? Anyone? We stumped y'all. So it would be a 4. Or actually, I'm sorry. A 4 would be the network ID. And 6 will be this address. And then a 7 will be the broadcast address.
So yeah, and maybe we should walk through that. You're probably gonna do that, right?
Yep. So network and broadcast address. So the network ID is 192.168.20.4. The reason that is because when it starts at 0, you have the other set of networks then to go in that /30. So with the /30 CIDR notation, it forces you only to use 4 addresses at a time. So 0, 1, 2, and 3 are on the other network. 4, 5, 6, and 7 are for the network that you're on now. So you only have 2 usable, which would be 5 and 6. And then when you're talking real world example, this would be like a point-to-point connection. You know, if you have one location talking to another location, and you have a whole bunch of addresses allocated, so you want to use the minimum number available. That makes sense? Any questions? No? All right, I'll move on. So next scenario, we have a company. We got a finance department, IT department, manufacturing area, sales and marketing. They all talk to a switch, and they're all on different networks, and they have a router that will make decisions based on what IP address they have, as far as who can talk to what. And then we have a line out to the internet. So you want to IP address these as a different IP address because, for example, you don't want your manufacturing guys to be able to talk to the finance and HR because you might get, you know, might get to, you don't want hackers to come into the manufacturing area, get on a computer over in, you know, a wood shop someplace, and then hack into the finance department and steal all the money, or change their HR to, you know, have a salary of $100,000 or something as a normal worker. So we want to separate these into different IP address ranges so that we can provide security ACLs on this router to prevent people from talking to one another, or only allowing who can talk to what. So in this case, or at least what I came up with, you can address them however you like. But this particular one, we just wanted to formulate it on department. So in this case, 192.168.00/24 will be for the network management. HR and finance gets 192.168.1.0/24. IT department 2.24 or 2.0.24. Manufacturing 3.0/24. Sales and marketing 4.0/24. Make sense? Yeah, seems to work pretty good. That would give you 255 addresses for each of these areas, and then you could use the router to route between all of them, as well as the internet, and then also provide security at the layer 3 level. Oops. I don't want to go back. So
let me ask a question.
Mhm.
What kind of address is this 192.168? What type of address is that?
you want to take a stab at it? No. So these are what's called private addresses, private IP version 4 addresses. There's actually 3 separate ranges available to you for private addressing, and they're not publicly routable on the internet. They're only for a local network. So you can plug them into a router and plug your internet into that router, and it will not talk out to the internet using that address. In order to do that, you have to do what's called a NAT, and we'll talk about that in another episode. But basically it translates between an internal, non-routable IP address and a internet routable one. There's different methods of doing NAT. Network address translation is what NAT stands for.
Will we have to figure out how to do this for like a test? Because this is really hard to like memorize and follow.
Okay. Well, that's the reason why we're going over all this. So you have a question or what aren't you getting?
Is this how it always works, or is this just one way to do it for this situation?
Well, that's the beauty of networking, is it's pretty loosely done. There's certain rules you have to follow, but if you follow the rules, then you can get away with just about anything you want. So in reality, though, this is, you try to do things in a way that is easy to manage. So in this case, I've got all these zeros, which is a lot easier to manage than, say, the previous example where we had like 252s and you had networks starting with 4 or 5, that type of thing. So
Yeah, so you make a good point. To just come up a little bit, you can do private or publicly routable ranges in your network. You're the network engineer and you're at a St. Martin's, or you're at a corporation or something. And if you choose one of these private ranges, like a 192.168, that's for the Class C range. A B is a 172.16 range. It's a 31. And in the Class A, it's a 10 net. And you've maybe seen a lot of 10 net. Or maybe this 192.168 with your home address, with your home wireless access point. But they use these because they don't route out. Everyone can use these. They're interchangeable. You can make lots of different networks, like with the 10 net, and nobody else or everyone can use this. But once it gets to the edge, you've got to convert it to a publicly routable address out to the internet. So you can use those, or if you were given a range that you actually had registered with the IANA, okay, then the IANA you would get registered. They would give you a range, and you would pay, your yearly fee to keep that registered for your company and your contact. And then you could, depending on if it was a B or an A class, you would then configure everything, and it would have a publicly routable IP address for everything in your network. And that's how they used to do it. Everything was publicly routable, and then they decided these private ranges could be used to extend the life of IP version 4.
I'm sorry, Mark, go ahead.
Does that help?
I wanted to add, not speaking for Daniel, but obviously when you see the technical numerics of all of this, it sometimes won't go deep, but I noticed that in the open source textbook that you guys have posted from Peter Cordell, it is granular enough that it actually covers everything that you just talked about. And I can also tell the rest of the class that after years of looking at how many things from radio through television to cable networks, you look at your radio bandwidth, what's FM, what's AM, those were all assigned frequencies. And we all know there are frequencies for the airport or for the police, or and those are also types of networks. And of course, when we got to the internet, so to speak, it grew so fast and by so many, tens of millions a day, that this idea of being able to assign standardized private networks, government networks, Comcast, as you said, uses the 10 dot, and most of us saw the 192s in our first routers. And so the idea of how those networks are assigned ranges is true, but the ultimate effect is to make sure that every single device on the net can still be connected, but still be identified in a way that makes it easier to switch, like telephones, like any other thing that we have. And if you get too stuck, I just recommend the class to just slow down and go look at the manual that you guys have posted, because it covers this in very specific detail. and it will help. I know, in fact, I'm even looking at pieces of it here. And if I get stuck, it's like when we were talking about doing the calculations and the CIDR and so on, all of that is covered in the open source book. So I'm just going to say, keep watching the slides, and then I'm going to get it. I'll get it. So
Yeah. So I'm just looking at the time going, okay, yeah, I got to slow it down here. Maybe I should explain a little more where we're getting this 1, 2, 3 number. So 192.168.0/24/24 will give you 255 or 256 not usable, but IPs. You know, you have to subtract 2, so it'd be 254 usable addresses. So what that means is this 0 is all of the IPs that are being used for the nodes. 2 of them, obviously, one of them is going to be the network ID, and one of them is going to be the broadcast ID. So 0 would be the network ID, and 255 would be the broadcast ID. And then this 0 and 192.168 are all parts of the network. So then if we do 192.168.1, that's the next address after 255 or 250, yeah, 255. It rolls over to 1.0. And so then again, we'll count all the way up from 0 through 255, and then it rolls to 2.0. And again, this is all in decimal, in binary. It all rolls into 1s and 0s. And so when they all line up as all 1s and then all 0s, then that's how it's that's how the math works on it. So and then of course, as we go, you know, 2.0 through 255, and then it rolls over to 3.0 to 255. So it only counts by 255 per octet.
Peter, if I can add to what your slide shows, obviously you guys have mentioned that the switches themselves can easily route traffic back and forth between its known networks and their assignments. So all the 192.168s, where it cannot just simply jump across the void through the internet, you know, to something else with those local addresses, but it does provide a way to give you a range for both security and for immediate communication. And by allowing the network addresses to be subnetted, then you can separate the important, you know, sales and marketing guys or H&R and finance who may have sensitive information. It allows the switch the ability to be programmed where you have limited access in either direction. So I'm getting the idea that the subnetting would have been a logical conclusion to people designing an expansive internet, because we don't want all of our addresses, you know, available worldwide to, you know, a billion people. I mean, it would make sense that we have local switching that protects the local IDs. And I see it as both a security and an expansion thing, where we all got used to, you know, millisecond times down to microsecond times. Now our networks inside a room are virtually instantaneous, where it didn't used to be that way in the beginning.
Yep, that's exactly right.
But that,
So like, for example,
Jonathan,
go ahead, Mark.
you said, sorry, you said switch, but if we have these different subnets for the HR, finance, and IT and manufacturing, that middle device there with the V on it has got to be a router. Okay.
Okay. Good.
Actually,
Yeah. Good point.
No, it's a switch.
It has to route between subnets. Otherwise, if this is a switch, then everybody needs to be on the same subnet. Like everybody's got to be a 192.168.0 dot something. Maybe they're the 0 net or the 1 net. And it, you know, let's pick the 1 net, and then HR, finance, IT, manufacturing, sales, and marketing department. They're all, you know, 192.68 dot or 192.168.1.123, whatever, 1.4, 1.5. They're all in the same subnet. They can't be on different subnets. If you are on different subnets, then you can't find each other, and you're not talking to each other.
Okay, I see what you're saying. It's symbolic to me. You're right. I'm looking at the one where the internet's connected to the switch, and then you've got your other device, which allows you to transport between each of those four. So I see, but like Daniel's question is, it kind of gives you a false sense of what device you're looking at. There's no way to identify that without learning what the diagrams and what the numbers mean.
Yeah. Yeah. So both of those have to be routers, basically. The round
In the
one
discussion that we're talking about, yeah.
Yeah, right.
What I really wanted to do is make those into VLANs, but that's for another day, I think. Unless you want to talk about them now, we've got time, I guess.
Yeah, we can talk about it.
So what you could do is you could put on a layer 2 switch here that would talk that has the capability of doing what's called VLANs, virtual LANs. So it is a identifier in the packet header for the layer 2 that has, I believe it's I can't remember how many bits, but there's 493 different VLAN addresses that you can do, or 4,093 different VLAN identifiers that you can do. So, for example, you could make network management VLAN 1, HR and finance VLAN 2, IT department VLAN 3, manufacturing VLAN 4, sales and marketing VLAN 5. And then the switch would just, all the people in HR and finance would talk only to HR and finance, and IT department would only talk to IT department, manufacturing would only talk to manufacturing, sales and marketing could only talk to sales and marketing, because that would not route between those VLANs. You'd have to go into the router and set them up to talk to each other.
Yeah, so you're saying you physically partition those ports on the switch to have a group of ports for sales and marketing and a group for manufacturing. And it's like you had 4 different switches, but you just used one switch because there was enough ports on one. So you just, through circuitry, you just separated them as if they were 4 separate switches. And
5, but yeah.
5. And the only way then for them to talk to each other would be to take one of those ports then on each of those groups of one of the ports in the groups that you've cordoned off,
Right,
and connect them back to the router. You'd have to have 4 connections back to the router, right?
Right. Well, you can have one connection and configure it as what they call a trunk port, which would then pass all of the VLAN traffic along it and send it all to the router, and the router would figure it out and send out the proper VLAN traffic to the proper people.
So the router still requires the routing portion, which means moving from one VLAN or subnet to another still requires that router.
Yep.
I don't know if that's confusing or helpful, but
Yeah.
it allows you to better utilize a switch that you've got maybe 48 ports on a switch. Yep. And you aren't using them all for each of these divisions. Like at St. Martin's, you got a couple people in every one of these departments, right? So they could all be on different VLANs and still all be on the same switch. So you only buy one switch.
Right, and you could even put other switches in each of these departments as well. You know, separate them out by floors in a building or something like that. And it would all talk on layer 2 until it hits the router, where it would then get translated to layer 3. But if you do that, anytime you have switch to switch communication, you want to trunk the ports. That way you can translate between VLANs and set up more VLANs in the sales and marketing or manufacturing or whatever department you want. You can actually break it out into even further VLANs if you like. Like I said, there's 4,093 of them available. So questions or anything? No? All right, so I guess we'll move on to my next example, or final example I've got, and then we can talk about other things, I guess. So we've got a similar network, except we don't really have the routing and switching and everything that put out there. We want to have things addressed by physical location. So imagine in the IT department here, we'll have a router that will route between all of these different buildings. And then we have our connection out to the internet. So it will route between all of these. And this is like a university setting. We've got classrooms here, we've got research labs, and we've got a data center that we want to communicate. And the IT department's kind of the hub for everything, all the wiring, fiber optic cabling, whatever. It all goes into the IT department. It's actually kind of how St. Martin's is set up, although we don't really have any research labs. Maybe the science building, maybe you could consider that. But, and we have several data centers. We have 4 locations for data centers. So let's provide enough addresses to meet current and future needs for each of these. So in other words, the research lab, they may get a grant and they may need to expand, and they'll have, you know, another set of computers to do research with. Or the data center may need to get expanded and have an extra set of servers, and you need IP addresses for all of those. Same thing with classrooms. Maybe the classrooms, they build a new wing of classrooms, and you got to have computers for all those classrooms. Maybe they're computer classrooms, so it's even more addresses than you normally need. So how do you provide enough addresses to meet your current and future needs? Well, most locations, you know, either medium-sized to large-sized organizations are going to go with that class A 10.0.0.0/8 address, which is a private address, and it gives you, I want to say, 16 million different addresses to play with. And it's more not really a are you going to use that many addresses in your organization? It's more of an organizational type thing. We'll get into it just a minute here. So for example, our classrooms, we could put on 10.1.0.0/16. So /16, what does that give us? How many addresses would that give us in a /16? Anybody?
It's like 65,536 or something like that.
Yep. So you can see here, we've got building number 1, building number 2, building number 3, and building number 4. That makes a pretty convenient method of assigning addresses, because we're talking numbers and addresses. So we'll make this one 10.1 because it's building number 1. And maybe we'll do 10.2 for building number 2 and 10.3 for building number 3, and so on. And then that way we would give 16 or 65,000 addresses for each of these locations. And then you could further subnet those into different departments, or however which way you wanted to. So let's 65,534 addresses with the -2. Does that make sense?
Cool. I see a thumbs up by Octavio.
I like the thumbs up, so that's cool.
Anyone else? Are you understanding how you would use like a private address and like a 10 or 172.16 or a 192.168? And again, you can use these private addresses. And why do we use them? Because all the IP addresses have ran out. So if you try and go and say, hey, I'm a new company, I want to get a range of IP version 4, you've ran out. So what they'll give you is they'll give you IP version 6. But since we're just talking about 4 right now, these are the options we've got. We can take a 10 net or a 172.16 or a 192.168, these different ranges from different classes. And you've got the IP version 4 notes on Moodle that lay out these different ranges. And you could choose any one of these and use these, each of them having, of course, a different amount of IP addresses per range.
And yeah, one thing I've definitely learned as an IT person is that you can lock these down pretty darn tight in, you know, like say you have a server stack that's only got 14 servers. Well, you can allocate 14 addresses in a subnet all for them if you want. However, I don't do that. Don't ever pin yourself into a corner that way, because guarantee you somebody's going to come along and they're going to want to add a server to that. And then you're stuck because everything else has been subnetted, and so then you have to go and redo the entire thing in order to make that work. So yeah, you definitely want, I've learned that you want to keep it a little bit loose. You know, you don't want to make it completely bonkers, but you definitely want to keep it a little loose. Otherwise you end up shooting yourself in the foot. So like that point-to-point example we saw in the beginning, if we thought that there might be another point that they're going to add to that at some point, then you might want to think about some other addressing scheme than that. But if it's only 2 points, then that's the minimum number you can do.
Peter, I would not want to put you on the spot, but in the example that you're giving with the 10.1, 10.2, or 10.3, is there a way for you to describe a process to where, let's just say theoretically, that a school was built and what we're seeing on the slide was the outcome, and that you've got it wired in pretty much the way that we see it? How would one proceed through a checklist? Let's say that they got their new equipment out of the box. Would you be able to describe a walkthrough where how those numbers got assigned? I mean, do you have to go through a particular process to make sure that the 10.1 is assigned or the 10.2? How do you get the 10 off that newly turned on piece of equipment? So I'm trying to oversimplify it maybe, but I don't know how to describe it to where we might see in our heads real time what happens when you plug it in and then what you do to assign it to get them all connected.
Okay, so in your DHCP server, the DHCP server has the ability to talk VLANs. And so what you would want to do is you'd want to put each of these buildings on a separate VLAN. And that way in your DHCP addressing, say, okay, anybody coming on VLAN 1, or yeah, I guess we'll name it VLAN 1. Anybody coming on VLAN 1 is going to get a 10.1.0.0/16 address. And anybody coming on VLAN 2 is going to get a 10.2.0.0/16 address, and so on. Also, by the way, in this scheme that I've got here, how many different locations can we do before we start running out of addresses?
254. Let's assume that 0 is taken.
Yeah, 200. Well, 255, but 255 is going to have an address missing. Same thing with the first one. It's going to have an address missing. So assuming you can do this, assuming your organization is smaller than 255 locations. But if you get bigger than that, then yeah, you have to do a different management scheme.
Peter, so
Yeah.
if is this under the same network? Like for Wi-Fi, we're going to be same SSID, or if each subnet has different SSID?
You can do it however which way you want. For example, these could all be in different physical locations. So you might have different SSIDs, like they might be in different cities even. And this could be, if you're a government organization, say, you might have your own personal fiber run underground between the buildings. And so, yeah, you might have a different SSID. Or if you want to have a centralized system to where you could set up one SSID, and then somebody coming from the classrooms in building 1 and going over to the research lab, their phone or their device would automatically pick up the SSID and be the same, and you'd be getting on the network the same way.
But don't they have to renew their IP addresses?
It would switch it to a different IP automatically.
I see. Okay, thank you.
Yep. Here at this university, I've got it set up to where you end up with the same IP address no matter what location you're at, and it's all the same SSID.
But this is
a little different than what we've got
that
set
could be
here.
confusing because other places it could be that the wireless access point just plugs into the switch, and so you just get an IP address within that building. So building 1 or building 3 or building 4 or 2 or whatever, wherever you take your laptop and open it up, you get an IP address on those subnets. But in your case, Peter, you have a special technology that changes the VLAN of the port to a specific VLAN for students or faculty or HR or something, no matter where they go. So that's another level of management that you can actually have it within switches now.
Yep. It's called a NAC system, a Network Access Control System. And basically it takes the MAC address of your device and associates it. And it says, okay, you're allowed on the network, and then it keeps track of where you're at. So it will record if you went into a classroom, or it will record if you went to the research lab or the data center. And whatever access point you're connecting to, it will pick it up and record it as a location that you moved to. And it will automatically just swap between access points and say, okay, you moved obviously from this one to this one. And it just keeps all their settings and everything. It's almost seamless. Anytime you have a pretty complex system, things can go a little wonky. So sometimes I've noticed where it doesn't like to release your address if you jump to another AP. So every once in a while glitches, but it fixes itself within a minute or two.
I think one of the most difficult times in my experience level is in learning networking is that when you learn about just the physical topology, about where the cables plug in and the porting, as you were pointing out earlier, with domains and with the discovery of shared cities or all those things, that idea of using VLAN or using associations was something that is sometimes entirely different from the physical topology, especially if you're grouping departments or grouping a specific type of work on their network.
Mm-hmm.
And so I had to separate the physicality almost completely from what, in the case you point out, the algorithms that are placed for the VLAN associations and all that are supposed to override whatever the topology is and say, you're now in this group, so that each time you check in with your MAC to a device, that device then has to compare that to whatever the algorithms are for the virtual network settings. And that was the toughest thing for me. It did take a little while for me to get past. As Mark was pointing out, walking to a room, I immediately think that I'm now on the auspices of that particular box or router that it's first connected to. And that oftentimes is a mistake, because that router then reports back and makes you part of a different structure, at least virtually.
Right. Yep. With the advent of VLANs, it brought the physical layer and it basically abstracted it a bit to where you didn't have to have a physical device physically separating networks together. We like to look at diagrams, and that it makes it more, you can make sense of it better. But in reality, the VLANs are what actually make things work really well as far as different security options and getting different IP addresses and that type of thing. So yeah, it just makes it work a lot better if you have everything on different VLANs. I don't have another example.
You made me think of a
There was
question though, Peter. I know I've just been kind of hogging the whole Q&A here, but the
I think
persistence of
everybody's
those.
just relieved that you want to talk.
Well, one of the things that's always got me, I'm still learning this, because the open source book is just amazing, but throughout, the persistence of an address, when you're talking about somebody that turns their phone on and off, their PC on and off, we take it for granted that oftentimes we get the same IP when we come back on, or the persistence of that IP, anywhere we go. Is there a way to kind of quantify that in a simplified kind of view? Because I know that in a perfect scenario where each time you turned on, you'd get a new IP, that's not true. I oftentimes see it repeat. So maybe you could talk a little bit about that.
Absolutely. Okay, so DHCP server will hand out addresses, and it kind of keeps track of who wanted to get an address. So it gives you a lease, and your device will then say, hey, I've got a lease until 8 days from now, and then 7 days from now it'll send out another request saying, hey, I'm still on the network, DHCP server, can you give me a new address or what? And the DHCP server says, yeah, just keep the one you got. Now then, as far as moving from one location to the other and having the same IP address, that has to be done through VLAN. So here on campus, you're assigned a certain VLAN using the NAC system, the network access control. So as a student, you'll be assigned a certain VLAN, which will give you a certain address, and you'll probably keep that address with the DHCP server. The DHCP server won't change your address very often. And with the NAC system, you're able to take that VLAN and go from one place to another, and it will automatically say, okay, you've moved from here to there, and it just keeps it all working. It's kind of a layer 2 technology, so our routing system is here in the library, and that routes between all of the different VLANs that we've got on campus and the internet. So we've kind of got a blend of what we've got here in this example and what the previous example was, where we had the different apartments, the layer 2 switch with the VLANs. So imagine this, except on a big scale between buildings. So like the sales and marketing would be in a different building than the manufacturing would be. And so say in our case, because we have a NAC system that keeps track of it all, a person in manufacturing has a device registered as a manufacturing person. He moves over to the sales and marketing building, and they would just give him a manufacturing address. He still couldn't talk to any of the people in sales and marketing, even though he's in the building. And so it's a good security model to have that. So he can get on network and he can get to the things he wants to get to or needs to get to in the manufacturing, but he's in a different building. So it's much better for this person and also for security, because he's only able to access the things that he's allowed to access. And that's what the network access control server will do for you.
Well, that leads me to yet another question.
Sure.
With the assignment of the IPs and the way that the network structure is done, there's been no mention of allocation of resources. And I'll give you an example. You have the pipeline coming in the university, and yet you could probably tell from a dormitory that there's a ton of people doing League of Legends or Twitch or homework, just a massive amount of bandwidth usage compared to the sparse, use of it across certain departments.
Right.
Is there any consideration of resource allocation in terms of how, first of all, you might trunk to different parts of the university, and whether or not you have like a concurrent user login issue? I don't know if you guys have to worry about that, but let's just say that everybody fired up on the same afternoon and at 2 o'clock, there's so many virtual meetings and so many people. How does that work, at least from your perspective?
Okay, so in the old days, or if you have a limited amount of bandwidth out to the internet, then yes, they had to set up things called QoS. And I'm not sure if we'll be talking about QoS in this course or not, but
I don't want to get ahead of you if you were. So
it's a way of, it's called quality of service, QoS. And what that will do is it marks your traffic and based on various methods and you get a priority. So if you've got something that's streaming media, that's going to be a little higher priority, because if it's not, it's UDP traffic, and so if you drop the traffic because of bandwidth congestion, it's going to stutter on your video, or your phone call is going to cut out. So, like I said, in past, you've had to set up QoS to prioritize traffic based on various factors, and it's a big subject.
okay.
But in our case, we've just, instead of trying to maximize the bandwidth usage, I guess you could say, we've just upped our bandwidth. Okay. In other words, we create a faster connection. So when I started here, we had a 500 megabit connection out to the internet. And typically we would hit 300 to 400 megabit. Every once in a while it would smack up to the ceiling on 500 megabit and stuff would start getting dropped. But if you've got enough bandwidth, then nothing will drop things. So then we bought a Palo Alto firewall, which allowed us to go to gigabit, which then really freed things up, and people started using the end network more after that. Streaming media got even more. So we started seeing averages of 600 to 700 megabit a day on average. And then we would hit occasionally, not very often, maybe once a month, we'd hit a gigabit and it would smack the ceiling and start dropping traffic again.
Oh.
So now we're up to 2 gig pipe out to the internet. And we have 10 gig links between the buildings and the library here. And so, yeah, there's very little latency and very little in between you and the internet as far as speed goes. The main speed limiter right now is the switches in the dorms are limited to 100 megabit because they're old switches. And so I'm working on getting those allocated to be a gigabit switch instead. So, and then of course your Wi-Fi, that's a whole other story, because in theory, the Wi-Fi we have is good up to about a gigabit speed wise, but when everybody's on it, the speed drops dramatically. I mean, I've seen speeds of down to like 5 megabit before, which is too low to stream 4K video. 4K video requires like 20 megabits or so, 25 megabits. So.
Well, that leads me to ask you again, this is all kind of new to me in terms of like the BYOD thing where a lot of the students now have got tablets and phones, and they walk into the arena where each of these pieces of equipment is given an assigned, ID. What about the idea of, say, an individual phone setting up as a hotspot? Is there a way that you monitor when an individual IP starts
That's
to act?
the hardest thing to check. That's the hardest thing to do, because at that point, in order to detect that, our system is pretty good with that. It will detect them, but we can't really mitigate it. We can't do anything other than say, hey, turn off your hotspots, everybody.
Right.
If you've got one running, you have to turn it off.
Okay.
We
It just struck me
we
as odd.
can't force them to turn it off.
Okay.
Just because of the way the physical layer of the frequencies and not work with the Wi-Fi. So yeah, somebody turning on a rogue access point like a Wi-Fi hotspot, or they bring in a router of their own, then yeah, that completely messes with the current system that we have. So, and there's not much we can do to fix it other than banning people from using them. So yeah.
Okay, my very last question, and I swear I'll leave you alone, is that if you're in a scenario, I appreciate that. If you're in a scenario where we do lose power and the university goes down, we talked about how each of the switches stores some information on them, and we talk about the persistent cache that they may maintain. But in the case where they're totally drained, what would be the recommended process for bringing them up, and how does that affect how these addressing issues? As I can see here, each of those departments would then be started back up again in sequence. Is there something that you would like to see happen in terms of how that sequence of startup would go?
All right. So what I would like to see is them never to go down. So,
Yes.
So in theory, yes, that's why you have battery backups. That's why you have generator systems to keep all these systems working, because for them to go down, it's a little dicey for them to come back up. So all of the switches and routers and all that, they have a configuration saved into flash memory. So it's non-volatile memory. So it'll keep its configuration from power off to power on. You can do it over and over and over. It's not a problem. Those are the most, I guess, robust, I guess you could say, to having a power blink. But the servers, on the other hand, the server systems, that's what really does not like to have your power cut. Just because of all the complexity built into them with the different disk arrays, and you've got multiple CPUs with multiple cores on each one. And then of course, everything's got to talk in an appropriate manner to load up the software and everything. So the key server in there would be the Dhcp server. And so if you have a power blink and your Dhcp server goes out, you're going to want to make sure that comes up normally. That's probably the big one, to make sure everybody's network is back up and running. Now, of course, I say this, but there are times where we've had a power blink and some of the network devices are not on a battery backup. So when the power comes back on, for some reason, they just get in a weird state. So maybe the power came on and came on a different way, or it was a brownout type situation where it was only partially on, or it went off and then came back on and went off and came back on real quick like that. Sometimes those devices don't like that very much. So you have to physically go in, pull the power, wait a few seconds for everything to drain out, plug it back in, and then everything's fine. That's my job.
Well, you know, when you're talking about all these net addresses and things, they come up as this is what you see, you know, in the window of the store, but you don't know how the store operates. And it's my impression that even if you know those numbers and what category they belong in, how do they get assigned the way they do? How do they act in relation to the rest of the network pieces? So, you know, what you said does help. It gives me a lot of information to deal with. It does
Oh,
make me
yeah.
wonder out loud, though, if there was somebody who's designing a program to copy all of the router configurations, so in case of a massive outage, then you could literally have a way to restore all of the configuration profiles to all of the big, you know, the big control servers. So
Yeah.
yeah,
Okay, so in the event if for some reason your configuration file on your switches went out, then yes, that would be a pain to type in everything by hand. So what you do as a network administrator like myself, you go in there and you make a backup copy of the configuration file. That way, if something did go catastrophically wrong with the switch, usually if the memory on it went, you know, if your config went bad on it, that means the memory went bad on the switch. So normally it's like a replacement switch is what the problem is, or the fix for it is. But if for some reason something got corrupted and your flash memory is still good, then you can actually go in with a console cable and apply a new configuration within a minute or two, assuming you've got that configuration on your laptop.
so I'm guessing that you three or you four there, your laptops are your most vital pieces of equipment in the entire room.
Yeah, I mean, it
Yeah.
comes in handy. I take it everywhere. It seems like whenever I go to a trouble call, no matter what it is, I always need a laptop. So I bring it with me on everything. That and my
Thank you, Peter.
toolkit too. So like crimpers and all that type of thing. Even if they're complaining that the Wi-Fi is slow, for some reason, I might need some tools. So I bring those two with me. So.
The threat of tools is always important to the equipment, I think.
Yeah.
When the equipment knows you're carrying it, it starts to act funny, so, or better.
Right. Well, invariably, if I don't have what I need, I got to walk all the way across campus in order to go get whatever it is to fix it. So yeah, it's much more efficient just if you have the tools that you need with you.
Thank you for the broad scope coverage, Peter. I appreciate it.
Sure, sure. Any other questions at all? I mean, we've got another 20 minutes or so we can talk. Otherwise, I don't know. This is pretty much my last slide as far as IP addressing goes. Any questions?
This is more generic question that
Uh-huh.
the type of the classes, is that depends on the router that you're supporting with, or the server that you have, or what decide the either class A or class B or class C?
Okay, so the classes came from either the IEEE or the IANA, one of the two, back in like 1980 or 1979, whenever they came up with IP addressing. They decided that Class A addresses are going to be the first octet, Class B addresses are going to be the second octet, Class C addresses are going to be the third octet. And that's how they allocated them to the internet, or to individuals to get onto the internet. So yeah, they gave a lot of universities and government organizations Class A addresses. So some of your big universities are sitting right now on a Class A address. They have 16 million internet routable addresses to play with in IP version 4. Here at the university, we've got actually 3 ranges that we use. We've got a range that has 4 addresses, a range of a Class C, which is 255 addresses, and then we have a partial Class B, which is around 4,000 addresses, 4,093 addresses that we have. So we have plenty of internet routable IP version 4 addresses to play with. So we don't really mess with IP version 6 much here at the university, which I think that's one of the benefits of working here. I don't have to really deal with IP version 6 much, but
the one that for the private IP address, for example, most of the private router they're using with 192, the class C, but the Comcast one coming with 10 dot something, which is class A, or the one of the company that I work with, they were using 172, which is class B. So I would assume those are decided by or on the router, or that was my question, inside of the house, or is that the network?
So your ISP, if they're a good ISP, because it's been where they've misconfigured things, they will not allow traffic using those IP addresses, like 192.168 addresses, or 172.16 up to 19 addresses, or 10.000 addresses. If you've got any of those type addresses, your ISP will drop that traffic. Won't allow it to route out to the internet. So,
well, yeah, Gary, you might be talking about which one do you choose? 192.168, 172.16, or 10.
Yes.
You can choose any of those. Any of those are available to you. When they say private address ranges, any group, company, lab can use those in any way they want and configure those any way they want.
Yep.
But of course, internal use only, so they can route all around in your intranet. But then going out to the internet, you're just going to have to set up network address translation to convert it to a public. So that's where Peter's talking about. So you got to have some public IP addresses. Sometimes if it's a small group, you may only need one public IP address, and that's your pool, and everything uses that public IP when it goes to that NAT server to make that the source address as a packet heads out towards the internet. But it might be a pool of a dozen or more. It just depends how you set it up, but you've got to have some public IP addresses to route out to the internet.
Right.
Oh, got it. So it doesn't really matter on the router. It's how you configure it on the internet.
It's up to
Yeah,
you.
the network engineer makes that decision, throws on the number. I want to use 10 net here, or 172 here, 168, or 192.168 here.
Right.
And they're all going to work, because when you configure on the router says, it just accepts that and says, okay, you just put it on my router interface. So that's what the network is coming out of this port.
And so, so the way I look at it is, if you've got a fairly small organization, you want to use 192.168. If you got kind of a medium sized organization, use 172.16/ I want to say it's 20 is the private range. I'd have to look it up. I don't know exactly what it is.
16 through 31. Yeah, those range. That range.
And then if you've got a medium to large organization, you want to use 10.0 something. And that's what we use here. It's just, for me, it's easier to use 10 dot something numbers. I can instantly associate an IP address with a VLAN number, and it makes things a lot easier to manage. Whereas a 172 address range, it probably would work around here. In fact, the previous network admin use 172 ranges all over campus, and I just personally find that hard to differentiate between all the different networks that we have here on campus. So I use a 10 dot address range, just because it's easier for me to manage and say, okay, in our case, say network ranges 10.200 through 210 are going to be for staff people. So like 200 would be a staff workstation, 215 would be an ITS workstation, 205 would be for the Abbey monk people, that type of thing. So it just makes it easier for me to allocate addresses and still give enough addresses that they won't ever run out. Whereas like you could have 172.16 dot, 1 through 128 for this group of people, and 129 through 256 through for another group of people, and subnet it much more closely. But to me, I can't do that kind of math in my head. So that's the reason why I chose 10 dot.
That makes sense with the classes. I know that if I'm looking like at Phoenix University or UCLA or some large company, even like Microsoft, if you're within a company network, that network could be all over the planet. And you could effectively use up a lot of the address space, even with a class A. Strangely enough, I wouldn't think it would have 1 million addresses, but what I don't have any experience in, which maybe I don't know if you two do, with the way that the government would allocate, if you're a .gov or you're a WashDOT or you're the CA, the California DMV, I don't know how they would learn to allocate their networks across a statewide environment, for example, that might represent kind of where you're going.
Yeah.
Right.
Yeah. In those ranges, which one to use? I just shared this IP addressing worksheet that's in Moodle that you can look at. And if you have a class C, like a 192.168 private range, then basically you could only ever have with each of those ranges, those subnets, 256. So 254 usable addresses, because you can't use a 0 in 255. So if we've got 1,700 students here and they all jumped on Wi-Fi, then you're not going to be able to use that for Wi-Fi. You only have 256, so you're going to run out. So you jump up to let's say you use a private range down here. So you one of these here, right? And so if you do that, then a class B can have up to 65,000 addresses. So you could use that, or an A, 16 million. So you'd have to use an A or a B, and you've got these private ranges with B and A right here that you could use and choose from internally. If you were very limited with just a small pool of public IP addresses, then do that. Another point about, and Peter, you spoke about this, is like, well, you got a fraction of a class B. Well, one of the bottlenecks is network address translation, translating from one of these private ranges to a public range. And so I think you put all of the students on a public range, right?
Right.
That range where you don't have to go through NAT. So instead of going through and getting translated, every packet translating out to the internet, instead of having that bottleneck of that network address translation server, you can just be publicly addressed with that fraction of a class B address, B range. And if you got 4,000 nodes there, so you address all the students with within that range. You got a publicly routable address, no NAT required. So you bypass that and go straight out to the internet.
And that's in fact how we used to do things. We put 4,000 addresses for the students, and that was perfectly adequate until the students decided to start bringing all of their Internet of Things with them. So we ran out of addresses. So now we do a NAT system for students as well.
So there you have it.
We manage, it's up to 6,000 devices here on campus that are in our NAC system.
Oh, okay. Yeah.
For 1,500 students. Figure that one out.
All right. Well, it's 2:20.
Yep. Time to get
got
going.
other questions, shoot us an email. And what I'll do is I'll on Tuesday next week, we'll continue on with some IP version 4. We'll talk about how we actually we'll take an example and we'll do that, start working on that network assignment for addressing specific like sales offices. And we'll start working on that and see how we do when you start thinking about it and figuring out how you would configure different devices on different subnets. Okay.
May I ask, are you, so Mark, are you referring that to the online lab that was on Moodle? All right, sweet.
Yeah. Right. So we'll go through that. We'll start, we'll explain it and walk through it, and then it shouldn't be too hard. It just gives you a good example of how you would subnet, and then we'll see, we'll explain more about that, more practical, real world, why I would use what you use. And I think Peter kind of delved into that, making it easy to understand. Because you got to troubleshoot it. Okay. Good luck this weekend. It's Snowmageddon again. It's sticking. I'm looking out my window. I got an inch or inch and a half here in Olympia.
Great.
So drive safe, and we will